In this video, we're going to be talking about chillers and variable frequency drives, otherwise known as VFDs. Now, where do we most often see VFDs? We see them in large commercial environments. For example, large office buildings that might have centrifugal chillers. And we see them connected to the chiller drive motors because, again, a chiller is a big component, but we specifically see them on the drive motors. We see them on condenser water pumps. We see them on the chilled water pumps coming out of the system. We can see them on ice machine chillers as well. We see them in any environment where we need to have varying loads. And the VFD is actual a module. It's not the actual motor itself. So when we're talking about variable frequency drives, we're talking about basically the power supply and the controls of the motor, of the actual drive motor. So if we go back to here, the drive motor is up here in the corner, but off on the side, we're going to have a VFD controller or the VFD itself. Okay, which might be just a box on a wall or in an equipment room someplace. We also see VFDs used in package cooling towers. For example, this drive motor that's on the fan is a VFD. We see them in large package units. If you open the package unit wiring compartment and see a module that looks something like this, it's going to be a VFD. And it usually has a programming interface. We'll go into that a little bit more. You're going to see them on the condenser water pumps. Some might be older, some might be newer, but a VFD can be adapted to existing equipment. This is an example of an ABB, that's the manufacturer VFD. So why do we use VFDs? It's all about capacity controls. We use them where loads in commercial environments vary with the time of day. Loads in a commercial building may vary with season. Loads in production, for example, ice making, might vary with demand. That's called process cooling, by the way. The choices for capacity control is important versus cost. So we have a couple ways to do capacity control. First, we can have multiple pieces of equipment and turn whole systems on and off as needed. Or we can use a single piece of equipment and control its speed and how much cooling it's providing. Chillers are expensive, so the more chillers we have, the more expensive the installation it is. And also additional equipment takes up more floor space. Floor space is a very valuable part of commercial real estate. People pay a lot of money for the floor space. So the less equipment we have allows for reduced mechanical space and more rentable office space. Okay, chillers are expensive. So again, the less equipment we have to purchase, the lower the startup and installation costs. So by using VFDs, we can control the motor's speed. And by motors, I could mean the drive for the compressor or the centrifugal chiller, the drive for the circulating pumps, for the condenser water or the chilled water. We can vary these speeds and we can reduce electrical costs. We can reduce the amount and frequency of maintenance. We can provide an increased level of comfort, and we can increase the efficiency of all connected equipment. So what does a VFD do? To put it simply, a VFD, or variable frequency drive, changes the speed of the attached motor by changing the frequency and the voltages of the power going to it. A motor's speed is directly proportional to the frequency of the current or power going into it. So there's a formula for this. The motor speed formula is revolutions per minute, that's the speed of the motor, equals hertz, that's the frequency of the incoming power, multiplied by 2 because there's a positive and negative pole, divide that all by the number of poles in the motor. An example of this, okay, let's say we have a 60 hertz, let's say we have a 60 hertz motor, okay, that multiplies out to 120. Okay, so 60 times 2 is 120, and we can divide that by the number of poles in the motor. Okay, and by the way, so 60 times 30 times 2 divided by 8. So if I have 30 hertz, it's 450. If I double this to 60 hertz, which is our normal, it's going to be 900. The 60 and the 2 is we multiply 60 hertz times 60, as we need frequency in minutes, because there's 60 seconds to a minute. We multiply the whole thing by 2 by positive and negative. So here, if we take the standard AC motor at the 60 hertz we would normally have in North America, and the motor has 8 poles. This is just an example. We take our 60 times 60 times 2, which is 7,200. We divide it by 8, which gives us the 900 RPM. So if I cut the frequency in half, we get down to 450. So again, our frequency is very important. Our imaginary motor is running at 900 RPM at 60 hertz, but when we reduce the frequency by 50%, we can run the motor at 450 RPM. If this motor is attached to a centrifugal chiller or to a pump, we can increase and decrease the capacity by altering the speeds of the motors. Motor horsepower is the amount of work a motor can do. Horsepower equals volts times amps times efficiency divided by 746. The efficiency of the motor comes from the data plate on the motor and is a manufacturer rating. Motors are not 100% efficient because anytime you use electricity, heat is generated. Heat is what affects the efficiency of the motor. Motor torque is another value we have to be aware of. Torque is what starts the motor shaft and load turning. If the load requires more torque than what the drive motor can provide, the motor will stall. Torque equals horsepower times 5250 divided by RPM. So again, torque, horsepower times 5250 divided by RPM. If the system requires more torque than what can be provided, the motor is going to stall. So what does a VFD contain? Most VFDs contain several basic components. You have a control hardware that includes gate circuits, voltage sensors, processors, communication circuits, and power supplies. You have interface hardware consisting of switchgear, transformers, suppressors, and input-output filters, otherwise known as I/O filters. You have some mechanical components such as fans, heat sinks, connections, and bus bars. The hardware components on the prior slide are matched to 3 major control sections of the VFD. First, we have a process control section. This controls the output of the VFD. You have a converter rectifier section. It converts the AC current to DC. You have an inverter section. It converts the DC back to a quasi-AC. So what does it do overall in English? Let's keep this simple. The VFD takes that incoming alternating current, the AC current from the street or from the power company, and converts it to DC, direct current. Based on the need and the control signals, the VFD then converts that DC back to AC with controlled frequency and voltage to handle the required loads and torque. The output power, we might call it a quasi-AC because it has varying frequency and voltage, is sent to the drive motor, and the motor sees it as an AC current. The varying voltage and frequency will change the size and the shape of the magnetic field on the motor windings, and thus will change the speed and torque provided by the motor. Now, all of this happens in milliseconds of control, okay, because the system has to respond very quickly to load changes, to voltage changes. The AC current coming in from the street is sometimes not all as stable as we believe it to be. We have several parts of a variable frequency drive. You have the enclosure, okay, the external housing that's designed to protect personnel from contact with energized components of the drive. It also protects the internal components from environmental hazards such as moisture, dirt, and dust. You have the terminal boards. Typically, there are three main terminal boards provided. You have a power supply to the drive that might be labeled L1, 2, 3, or RS and T. You have a power to the motor, T1, T2, T3, or U, V, and W. You have connections to various control input and output devices. That's known as I/O. This is an example given to us by ADD. It's one of the variable speed drive manufacturers. And you can see where we have our analog and digital inputs, relay outputs. We have our panel connectors. We have some LEDs. Okay, we have some communication lines. And then we have our power output to the motor. This one is labeled U2, V2, and W2. And then we have power input, U1, V1, W1. Okay, you may have an EM1 and a PE. You have a grounding strap. Okay, and then you might have some terminals that are not used, usually for future expansion or for additional different types of components because they use one standard cabinet. Okay. You usually have a keypad. Okay, the operator can manually enter instructions into the VFD software program. It can also be used to retrieve statuses of the control program and data sets. You have LEDs. The face of the VFD may have several LEDs to give status information regarding the condition of the drive. You have communications. It allows for external communication with other control components using Ethernet or IP, Modbus, MATESYS, and other proprietary standards. This is just an example, again, from ABB of an HVAC VFD control panel. Okay, you have statuses. Okay, it's green when normal or red flashing. Okay, you have key presses where you can interface with the software. You usually have on-off switches, and sometimes you have help buttons. Okay, it allows language selection. Okay, drive connection that can be made or detached at any time. Has a startup assistant to facilitate commissioning, and has a real-time clock and some context-sensitive help. Every manufacturer's controls are going to be a little bit different. There is not a standard on what's available, so it's very important to read the manufacturers. So the HVAC control panel modes are simple. Okay, you have standard display mode. Okay, this is when everything is running normally. It shows drive status information and operates the drive. You have a parameters mode. You can edit the parameter individually. You have a startup assistant mode. Guides the startup and initial configuration. You can change the parameters mode. It shows changed parameters. You have a fault logger mode. It shows the drive fault history. Very important for troubleshooting. You have a drive parameter backup mode. It can store and upload the last parameters. Again, important because if you need to change out the VFD, you want to be able to just reload your existing control sets. You have a clock set mode. Okay, sets the time and date for the drive. You have an I/O settings mode. Checks and edits the I/O settings. You have an alarm mode that reports. It's a reporting mode triggered by drive alarms. Diagnostic displays are also available. The drive can detect error conditions and report them using the green or red LED on the body of the drive, the status LED on the control panel, and the control panel display. This could be done as a fault word and alarm word parameter. The form of the display depends on the severity of the error. You can specify severity on all controls for many errors by directing the drive to ignore the error situation, report the situation as an alarm, or report the situation as a fault. A red LED with faults signals a severe error. Okay, it sets the appropriate bit word on the output, and it overrides the control panel display to display the fault code, and sometimes it will stop the motor. External inputs are available on most variable frequency drives. Okay, they're capable of using some external inputs to change the VFD operation. These inputs can either be AC or DC signals that could be a range of 4 to 20 milliamps or 0 to 10 VDC, that's voltage DC. Now, these happen to be the same ranges that are found in most building control systems. You can have all VFDs have a converter section. The converter section takes the AC signal to DC and routes it to a DC bus. This is typically done with rectifiers or diodes. Rectifiers and diodes allow power to pass in one direction only. They smooth out the power to make it appear as a DC signal. Okay, what it does, so we have two sides of it usually. We have a positive and a negative. The positive side takes the AC input signal and only passes the side that's on the positive side of the sine wave. The negative side passes the side that's on the negative side of the sine wave. So on the DC bus, I have a true positive and a negative supply. The inverter section then takes that DC signal from the DC bus and switches it on and off. The on-off switching is timed to develop the quasi-AC sine wave. This is accomplished in most modern VFDs by using something we call an insulated gate bipolar transistor, IGBTs. These devices can switch at 5 million times per second. By using these high-speed devices, the VFD can develop an output waveform that closely follows a standard AC sine wave, but at varying frequencies. Now, we've mentioned it a few times, but all of the VFDs contain a DC bus. The DC bus smooths out the pulse power produced by the converter section. The DC bus usually includes filters and capacitors. Now, it's very important as you work with VFDs to realize VFDs generate heat. They generate heat as they operate, and that needs to be taken into account when they are installed and maintained. There are fans in the VFD enclosure that must be operational for them in order for them not to overheat. Max temperature of most VFDs is 120 and I'm going to add to 160 degrees Fahrenheit. On a hot summer day in Miami, Florida, if these are installed in a non-conditioned space, they can overheat and melt down. You do not want to install these in direct sunlight. The heat generated varies with the drive size and voltages. For example, one manufacturer specifies a 460 volt drive. 1 horsepower equals 82 BTUs per hour. Then if it goes up to 20 horsepower drive, it's 1163 BTUs per hour. Another manufacturer may have entirely different values. For example, 5 horsepower is 561 BTU per hour. So if we take a centrifugal chiller, for example, that's 20 horsepower with 2 pumps that are 5 horsepower each, okay, we add up the 1163, 320, 320. So the total heat produced by just the VFD for this chiller is 1803 BTUs per hour. Now, to put that into retrospect, 1 ton of cooling is 1200 BTUs per hour. This number, 1803, has nothing to do, doesn't even include the heat of compression, the heat produced by the hot water piping that's running through there. That's the condenser water piping. The heat generated by the actual drive motor. Okay, it just includes the VFD. So there's a lot of heat generated by some of these systems, and you have to account for that in cooling. Now, VFDs do need to be maintained. It comes down to keeping it clean, tight, and dry. Moisture and dirt are the most frequent causes of VFD failure. According to several manufacturers, maintenance should include some basic checks. Checking and recording the voltage on the DC bus. Check the temperature of all main and motor terminals. Make sure you investigate any difference between the terminals of more than 5 degrees. Inspect all electrical capacitors for indication of swelling, arcing, or leaks. The microfarads of all capacitors need to be tested and should be within 5% of the rated microfarad. Remember to isolate components and only test capacitors after they have been discharged. Inspect ventilation fans for bad bearings, loose or damaged fans, and replace as needed. Inspect, clean, or replace as needed all air filters. Record the ambient temperatures. Record the supply voltage with the motor operating at a rated load and speed and then also unloaded. Record voltages L1 to L2 and L1 to L3 and also line to ground voltages. You might also have a manufacturer maintenance intervals. Again, this is recommended by ABB, which is one of the controlled manufacturers. So they recommend that you replace the inlet air filter every 3 months. Okay, you check or replace the exhaust air filters every 6 months. Check and clean heat sinks, okay, every 6 to 12 months. And again, they put a note, depends on the dustiness of the environment. Check cable connections are secure and tight every year. Replace the closure fan every 3 years. Replace the drive module fan every 6 years. Change the capacitors every 10 years. Replace the battery in the assistant control panel every 10 years. So each manufacturer has maintenance intervals for a lot of their equipment. Okay, and notice where it says as needed, okay, for replace, but down here it doesn't tell you as needed. Okay, so you do it. And of course, if you see a problem where something doesn't test out, you do it earlier than what they're saying. The use of IR imaging can allow you to take temperatures of all components without using contact thermometers. Comparing your voltage readings to commissioning readings, that's at startup, and prior readings can alert you in advance to problematic changes over time. So you want to document everything for future use. There's a tremendous amount of electrical current and voltages in play within the VFD. Be very aware of arc flash hazards and use personal protective equipment. Always, always, always use lockout tagout when operating within a VFD or any attached equipment. Some high voltage and electrical hazards and faults can cause an arc flash. Okay, these two pictures over here are an example of an arc flash that happened within a VFD. This is an example of a surge that caused a meltdown of the connecting lugs for, it happened to be L3 on a VFD. So be very aware of the high voltages and what can happen. If this had been in someone's face without a PPE, they would have probably been in the hospital or worse. There's no automatic way to troubleshoot VFDs. Okay, it takes your tools, your meters, and a high degree of human intelligence, otherwise known as HID. Okay, you must be systematic in your approach. You have to do it the same way every time so you don't skip everything. Do not ever stop at the first problem you notice. Keep going. So if you notice a loose connection or burnt terminal or burnt capacitor, you have to keep going. If a VFD breaks, you must find the cause or it's going to happen again and again. A VFD sometimes having a problem is a sign of other failures. Document everything with pictures of your readings, write down your readings so you're able to compare them to the baseline commissioning readings or the last maintenance readings. We have to talk about safety and troubleshooting with VFDs because you have to be very aware of the voltages. Many VFD operates at 460 volts AC. The peak voltage can be 1.5% higher, leaving the DC voltage upwards of 670 volts DC. A motor then located, that's the output of the unit. A motor located about 50 wire feet away from the control can see voltages between 998 and 1231 volts. If possible, always have someone close by that is ready to provide aid. Try not to check energized VFDs on the motor side unless you have somebody close by. If they're energized especially. Know your meter. The voltages in VFD systems can easily exceed what your meter is rated for. It can exceed what the leads are rated for. Do not assume your meter can handle it. No. Always check the documentation for your meter. Okay, I have one meter that I use that only can handle 600 volts. Well, I obviously am not using it on VFD systems. Use the one-handed approach to troubleshooting. One meter lead is connected to a fixed point with a well-insulated alligator clip. The second lead is moved around in order to test voltages. Amperage readings are taken with a clamp on, one-handed. By using one hand, it prevents the path of current through your heart if you come in contact with the current. Be ultra cautious with any system with a VFD. Readings you want to take readings of the AC voltage to the drive. You take L1, L2, L3. Then you go L1 to L2, L1 to L3. You go L1 to ground, L2 to ground, L3 to ground. You want to take amperage flowing to the drive. Again, L1, L2, L3. You want to take a voltage reading of the DC bus voltage. Then you go AC voltage to the motor on each terminal, AC amperage to the motor on each terminal. T1 to ground, T2 to ground, T3 to ground. Amperage on T1, T2, and T3. OSHA requires the use of double insulated gloves on your hands when troubleshooting live equipment, especially VFDs. The voltages are considered class 2. VFD drives are especially sensitive to current and voltage imbalances. A current imbalance of 3% can result from an overheating of motor. What do we mean by an imbalance? Imbalance is where I have different voltages on T1, T2, or T2, T3. Okay, in other words, if my supplies are giving me different voltages, we can overheat a motor. Voltage imbalance equals the maximum deviation from average divided by the average voltage multiplied by 100. An example of this could be a reading of 35, 30, and 3. These are amps. Gives me a 31.7 average. The maximum deviation from the average is 3.3 amps. 3.3 amps is 10.4% of 31.7 amps. High voltage surges can occur when one or more of the phases entering the drives. Okay. Voltage surges are especially dangerous for operation and lifespan of the VFD drives. Surge suppressors should be used prior to the drive. Surges can cause internal fires, arcing, and damage to the components. Surges can increase the voltage faster than the control components can respond. They also cause massive phase imbalances. There's special notes that need to be talked about when we're using Meggers and VFD drives. One common test, or should be a common test, is the use of a Megger to test the motor windings. Meggers are capable of creating a DC voltage as high as 1500 volts. Voltages in that range will destroy solid-state components within a VFD. Connect all drive leads from the motor before testing the motor. You do not want any voltage that high to go back into the VFD itself. So you have to disconnect all leads before testing the motor. Should be doing that anyways because you're ohming something out. The component should be isolated.